PAL, programmable array logic. Another is PLA, programmable logic array. Then we have CPLD, complex programmable logic device. And we also have FPGA, which is full programmable gate array. Full programmable gate array. As I mentioned, that programmable ROM is also can be used as a programmable logic device, PROM. So in case of programmable logic device, it actually consists of an AND array and a OR array. So this PLD consists of an AND gates array or array of AND gates and an array of OR gates. And there is an interconnection between the input and array of the AND gates, and then there is an interconnection between the array of AND gates and array of OR gates. Then finally we will get our output here. So the PLD consists of array of AND gates and an array of OR gates. And there is an interconnection between the inputs and the array of AND gates, and there is an interconnection between the array of AND gates and the array of OR gates. This interconnection, in case of PLD, this interconnection between the input and the array of AND gates, this is fixed. This one is fixed. Whereas the interconnection between this array of AND gates and the array of OR gates are, it can you can fix or you can program. Okay, so by programming these interconnections, we can do various kind of operations. If you want to run adder circuit, we can do that. If you want to express any Boolean expression, we can do that. If you want to make it a conversion circuit, binary to gray conversion, we can do that. So by changing that interconnections, but this interconnection will remain fixed. So from whenever we at the very beginning of this course, we talk about various kind of circuits, and we found that, like we talk about the adder circuit, subtractor circuit, then we talk about some Boolean expression, logical functions. We saw that all of them output are a combination of logic circuit that can be expressed in terms of SOP, like sum of product form. All of them are actually expressed in sum of product form. So if we go back to those functions, one of the functions was full adder circuit, right? Can you remember the full adder circuit? The full adder circuit, it is an XOR gate, then you give it to the another XOR gate. So this is my sum output, right? And then you will give it, take it to the two input to the AND gate, then take another output here and output here, sorry, carry. Then OR gate. Right? So this was our full adder circuit. And if we have the write down the expression for the sum operation and the carry operation, it was A bar B bar C in plus A bar B C in bar plus A B bar C bar in plus A B C in. And if we have done for the carry, it was A bar B C in plus A B bar C in plus A B C in bar plus A B C in. So this is a sum of product forms, right? We have the OR function here, OR operator, and this is the AND operation. So we need some AND gate, we need some OR gate to perform this things. In the PROM, the programmable ROM, the AND gate is fixed, while the OR gate array is programmable. In case, as I mentioned, in the programmable logic device, we will have PAL, PLA, CPLD, FPGA, as well as the PROM. PROM is all kind of a programmable logic device. In case of this PROM, this array, so we have AND array, and we have OR array, we have input here, we have interconnection here. In case of PROM, this AND array is fixed, and this is programmable. This array is programmable. Okay? So, at first again I am repeating, in case of programmable logic device, it consists of two things. Array of AND gates, array of OR gates. So if you go back in our last week, we talked about the ROM, right? Programmable ROM. So if I want to draw the block diagram that 8 times 4 ohms, in case of 8 times 4 ohms, we should have a decoder, right? A decoder circuit, 3 to 8 decoder circuit. These address lines can be used as an input. These are the address lines. And also we have an enable input. Then we have an 8 outputs, right? Zero, 1, 2, 3, 4, 5, 6, 7. 8 outputs. Then we have so these are the interconnection. And we can take the output of the decoder circuit to the OR gate. We actually have interconnection. We have what? We already saw, we have a MOSFET. And whenever it is a PMOS, we have a fuse. And the fuse is connected between the source terminal and to the column. If I draw this one, so it was something like this. So that is some fuse. There is some fuse. There is some fuse. So these fuses are connected in between the source terminal. This is the source terminal to the column. So at every connection, we have this connection. So at the very beginning of the PROM, we have all ones. Then according to our requirement, we just apply a very high, huge amount of current so that we can burn it. So whenever we burn it, it will become 0. Otherwise, all the connections will be intact, either burned or intact. Right? So at the very beginning, it will be intact. That means it will be all logic 1. Then according to our requirement, we just apply huge high amount of current and we can burn it, we can make resistance. Okay. So we can say that in programmable ROM or PROM, it consists of a decoder circuit and a memory cell. So this is a decoder circuit and this is the memory cell. Inside the memory cell, we have that MOS circuit and the fuses. So 8 by 4 ROMs, we have total how many words? 8 words. Of course, we have total 8 words and each word consists of these bytes. Here, each AND gate represents a specific minterm. So if you look at this 3 to 8 decoder, so
that E is the enable pin?
E is the enable pin. Yes, E is the enable pin. I just want to show you just for 1 second. So if you look at that, yes.
Address, what's?
Address line, sir.
Address.
I'm sorry for my handwriting. So in the 3 to 8 decoder circuits, we have 8 outputs, right? And those 8 outputs actually, then we have 8 AND gates. So you can see, can you see the figure? So this is the 3 to 8 decoder, right? And we have these internal structures of these 3 to 8 decoders. So we have 3 inputs, we have 8 outputs, we have 8 AND gates. Each AND gates are input consists of 3 inputs. So that means each output of each AND gate is a min-term. Each min-term. So you can say that each AND gate represents a specific min-terms. Okay? So I just want to show you so that we can, because long back we talked about these things. So now come to here about this programmable logic device. We are talking about the zero. So in the decoder circuit, the interconnection between the input and output AND gates are fixed. So as you mentioned, in case of PROM, so we are talking about PLE. The PLE consists of array of AND gate and array of OR gate. So this array of AND gate is fixed inside the decoder circuit. As I mentioned in PROM, this interconnection will be fixed and this interconnection will be programmable. So this interconnection of AND gate, array of AND gate is fixed inside our decoder circuit. So this is the array of OR gate. Now, according to our requirement, we can actually program it. Okay. So in 8 to 4 ROM, each gate consists of 8 inputs. So for example, if I choose some connection like this, according to our program, let me use another color. So
Those are all NAND gate, right?
here,
NMOS. Those are NMOS, right?
this is NMOS. So because we have drain, gate, resource. So for example, we have interconnection like this. This 1, 2, 4, 6, 2, 4, 6, and this one, So for example, we program like this. We have done some interconnection. So these are interconnected here. Other are actually just. So the second OR gate. So this is the second OR gate. So we can see that in the second OR gate, it has a connection from 3 different min-terms. 3 different min-terms. M2, M4, M6. Similarly, for first OR gate, it has min-terms for 1, 2, 3, 4, 5. M0, M2, M4, M6, M7. I just randomly design it. For example, they will give you some functions. Similarly, for D3, we have 6 different min-terms: M0, M1, M2, M3, M4, M5, M6. So we can design accordingly. So we can write down the function F3, that means for D3, function F3 is the min-terms of 0, 1, 2, 3, 4, 5, 6. Similarly, for function F2, after entering this D2, so this is min-terms, SOP, right? So it will be 1, 2, 4, 6. Min-term 2, 4, 6. For function 3, this is output of this given OR gate. It has 1, 3, 5, 7. So min-terms 1, 3, 5, 7. And finally for the F4 function, min-terms are 0, 2, 4, 6. 0, 2, 4, 6, 7. So if the functions is given, if examples is given like this, you have to design the circuit like this. According to the functions, you have to make the connection between the output of the decoder to the power gate.
And the function can be anything.
Yeah, function can be anything. Okay? So this is a random. So by using 8 times 4 theorem, we can implement the 4 different functions of 3 variables here. We can implement 4 different functions with 3 variables. Because we have 3 variables here. So it has a function, this one. So we can have different functions.
If it's 4, then 2 to the power 4, 16?
No.
Sorry.
4 different functions.
No, address line.
Address line is 3. So 3 to the 3 means 8.
8.
2 to the 3 means 8.
If
8
it's
possible
4,
functions. So each of them, so that means you have to from 0, 0, 0 to 1, 1, 1.
yes.
Any combinations.
No. I'm saying if there is 3 address line, 2 to the power 4, right? Then that's how many we are going to.
No, 3 address lines.
If it's 4 address line.
2 to the power 4, 16.
16.
16. So it will be 16 times 4 pure. 16 times 4 pure. So 4 Boolean functions of 4 variables. In case of 16 times 8 pure, we will have 8 Boolean functions of 4 variables. Okay. So let's see. Once we go to implement some circuit, then it will be more clear to us. So at the beginning, as I mentioned, for example, if we can talk about that full adder circuit or the full subtractor circuit. We already talked about how we can have a circuit that will perform both the adder and the subtractor circuit, right? In our exam, we also do that. So if you want to implement a full adder and full subtractor circuit, if you have to design a programmable logic design that will perform full adder and as a full subtractor. So if you know what is the full adder circuit, in the full adder circuit, how many inputs we have? 3, A, B and carry. So we'll have 3 inputs, A, B and carry. How many outputs? Sum, carry. In the full subtractor circuit, 3 inputs, A, B and borrow, right? Here, difference and the borrow. So you can see here, if you want to implement a full adder circuit, you need to output 2 functions, a sum and a carry. And if you want to implement a full subtractor circuit, you want to output difference and the borrow. So we need 4 different functions. And here we have 3 inputs. So we can implement this full adder and full subtractor circuit by using into 8 times 4 theorem. Because in the 8 times 4 theorems, we already said that we can use 3 address lines for the 3 inputs, and we have 4 different functions. So one of the function will be sum, another functions will be the carry, the third functions will be for difference, and the fourth functions will be for the borrow. So how we can implement these things? To implement these things, of course, we need to see the truth table first. According to the truth table, then we can find out our mean terms. And according to our mean terms, then we can select which interconnect should be intact or which interconnect should be barred. So let's see. If you see, look at the full adder truth table circuit. If we see the full adder truth table circuit here, I just draw very fast here. So A, B, C in, then sum, and the carry, right? So we have 3 outputs, so 0, 0, 0, 2, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay? Everything? Right? Okay. So we already know for the sum operations, sum will be high. So it will be high for this one, for 1, 0, 0, this one, and for 1, 1, 1. And for carry output, we have for 0, 1, 1 here, for 1, 0, and last 3. So this is my truth table for the full adder circuit. This is sum output. So we have sum output. We have 4 different minterms which has high for sum 001, 010, 100, 111. So we can say the minterms for sum output for sum function S is equals to minterms which one? 1, 2, 4, 7. 1, 2, 4, 7. 1, 2, 4, 7.
Fs means sum output.
Sum. Function for sum. Similarly, for function for carry, Fc, we can write down Fc equals to the midterms for carry output. We have midterms 1 for 4 different midterms. We have high output for 4 different midterms. Which one? 3, 5, 6, 7. 3, 5, 6, 7. 3, 5, 6, 7. Okay? Similarly, if I want to get the truth table for the borrow and the difference, so just let me remove these tables. Now I will say this is difference and this is borrow and this is also borrow B in. So we'll see the difference output is high on logic 1 for 4 different midterms which are 1, 2, then 4, then 7. And for the borrow we have 1, 2, 3, 7. 1, 2, 3, sorry. 1, 2, 3, and 7. So we can write down the function f d is equals to midterms 1, 2, 4, 7 and fb borrow function for 1, 2, 3. So we already have our functions. So we need 4 different functions and we have 3 inputs for both cases. So we can just implement this full adder and full substitute circuit by using 8 times 4 theorem, right? So if you just, now you have to draw this one.
This is for full
Adder and full substitute.
full substitute.
So if you have this one, again, 1, 2, 3. So here we give our input and we see in our borrow here. This is the enable input. This is 3 to 8 decoder. Again, so 0, 1, 2, 3, 4, 5, 6, 7. We have the output. Right? So we'll have D3, D2, D1, D0. Now, according to this midterms, we can just select, right? So if you think that we want to use this D3 for borrow, yeah. So this is for the difference and the borrow, for the substitute, and these two for the, so it's up to you. We can choose anything, right? We can choose anyone. So for example, we choose these two OR gate for adder circuit, these two OR gate for our substitute circuit. So for our adder circuit, what we have for the adder circuit? Sum 1, 2, 4, 7. So 1, 2, 4, 7. So for example, 1, 2, 4, 7. So it will give you full Fs. Sum. For the carry 3, 5, 6, 7. So 3, 5, 6, 7. So it will be carried. Now for the subtractor 1, 2, 4, 7 for the difference 1, 2, 4, 7. 1, 2, 4, 7 for the difference, and for the borrow 1, 2, 3, 7. 1, 2, 3, 7. So we can easily design the full adder and full substitute circuit together by using this 8 times 4. So you have to design something like this. You have to design a full adder or full substitute circuit by using the 8 times 4 theorem. Or you have to give it some functions like this. You have to just implement by using the theorem. Okay? Okay. So we can easily get our truth table for this one. So from here we can actually get a final truth table for our theorem. So what will be the truth table will look like? So the truth table will be for the theorem. So we have input 0, 0, 0, 2. This is my inputs. And my outputs, we have 4, right? D4, D3, D2, D1. So now D3 is for difference 1, 2, 4, 7. So 1, 2, 4, 7 will be 1. 1, 2, 4, 7 will be 1. If I use a different color, 1, 2, 4. Sorry, my mistake. 1, 2, 4, 7. For D2, D2 is my borrow 1, 2, 3, 7. 1, 2, 3, 7. And for this sum, D1 is my sum output. So 1, 2, 4, 7. 1, 2, 4, 7. And last finally carry 3, 5, 6, 7. 3, 5, 6, 7. So this will be the final output. For example, if you have this IC, programmable IC, which can perform your full adder and full subtractor, it will give you the truth table. So it will perform according to this. So from the truth table, you can design from the function mentions, you can design. I didn't put the zeros, all others are zeros. So you have to, that means you have to keep intact those fuse, and other fuses will be bottom. So that means you have an interconnection between the output of the decoder circuit to the OR gate. Here we have 4 midterms, here we have these 4 midterms, here we have these 4 midterms, and here we have these 4 midterms. So this SOP can perform as a full adder and full circuit. Now, for example, you have this 8 times 4 kilo. It is for adder circuit and full subtractor circuit. Now we can also reprogram it for binary to gray conversion. Right? So if you want to do that, what you need to do? You have to know the truth table for the binary. So usually we can have n number of inputs in the binary output, and outputs we should have n number of gray output codes. So if you want to make if I ask you to implement a 3-bit binary to gray conversion by using 8 times 4 kilo, implement a 3-bit binary to gray code. 3-bit to binary gray code. So if you want to implement 3-bit binary gray to binary to gray code, that means 3 binary bit. We will have 3 binary bit. 3 binary bit, which will be B2, B1, and B0, right? This will be the MSB, and this will be the LSB. For this, we should have a 3-bit gray code. So 3-bit gray code, 3-bit gray code, G2, G1, G0. Can you remember how to get this G2, G0, and G1? G2 will be same as B2. G1 will be XOR of B2, XOR B1. And 0 is XOR of B1, B0. So we have 3 inputs binary. So this is the 3 inputs binary still, right? So now if I remove this previous data, now I am changing the interconnection, the fuse, right? I am reprogramming it. I am just reprogramming it. So G2 will be exactly by B2. So what is B2? So B2 is my MSB. So here, so it will be just, so we can use any of the OR gate. As we need only 3 gray code, we can use any of them. So we can use starting from here to here. So we can say, so we have this B2, so this is B2, B0, B1, say we call it G2, G2, G1, G0. As G2 will be equals to B2, so B2 will be here, so we have 1, 1, 1, 1. For G1, as I mentioned, it will be B2 XOR B1. So B2 XOR B1 means 0, 1, 0, 1, 1, 0, 1, 0. These are the 4, right? These are the 4. So 0, 1, 0, 1, 1, 0, 1, 0. Because 1, 1, 0, 1, 1, 0, 0, 0, 0. So these are the 4. For G0, B1 XOR B0. So B1 XOR B0. 0, 1, 1, 0. So not 1, 1, no 0, 0, 0, 1, 1, 0. Right? So it will be, so G0, now we can say G3 is the midterms of, sorry, G2, not G3, sorry. G2 is the midterms of 4, 5, 6, 7. 4, 5, 6, 7. G1 is the midterms of this one. 2, 3, 4, 5, right? 2, 3, 4, 5. 2, 3, 4, 5. And G0 is the midterm of finally 1, 2, 5, 6. 1, 2, 5, 6. So you get your functions. Now according to your functions, you have to make your interconnections, right? Either will keep you intact or you will burn it. So you will keep intact these ones and other rest of them you will have to burn it. So if I go to here, okay, so if you are using this 3, so you can use this 3. So 4, 5, 6, 7. we can just 1, 4, 5, 6, 7. Four, 5, 6, 7, 4, 5, 6, 7. So it will give you now G2, G1, G0. So 2, 3, 4, 5, 2, 3, 4, 5, and last one 1, 2, 5, 6. 1, 2, 5, 6. So we can implement this way. And you have to draw the circuit to implement this. Okay? You don't need to show the truth table. You can just, if you can, without the truth table, you have to write down the function, and then according to the function, you have to show the interconnectors. So here, this is a PROM. As I mentioned, the PROM is also a one kind of programmable logic device, where the AND array. So programmable logic device consists of an AND array as well as an OR array. There is an interconnection between the input to the AND array, then there is an interconnection between the AND array to the OR array. In case of programmable logic PROM, programmable ROM, the AND array will remain constant. The AND array actually inside our decoder circuit. This OR array will be programmed or fixed. Okay? So now we will design.
So an array is just in the encoder, and this is the array.
Or array.
There is also an array inside.
An array inside. Okay. And this is the OR array. So after the second exam, we studied for the final exam. I think it's CMOS, right? CMOS. So in the final exam, we will have questions from CMOS. Then we will have questions from this memory, RAM and ROM, and this PL and PLD, something like this. So this is the syllabus. So we are almost done with our courses. Maybe by next week we'll finish, and we'll just slowly will go. Then on the final week we'll see what we can do. Maybe we can review if you have any questions, okay? And we'll talk about it. And some of you Rockhurst students have some issues. So I need to talk with my admin, and I ask you to talk with your advisor how we can fix these things as you are graduating on 10th of May. So if we can take the exam early or not, I need to talk with my division head, and you also have to talk with your, and let me know together. You are 3 students, right? You, Melanie, only 3, right? Any of you are here from Rockhurst? Only 3. Okay.
So when is the final week?
Final exam
Is it
or final
13?
week?
Final week, both.
Final week is the first week of May, right? First week of May is our final week. And the final exam, if I'm not wrong, it is already mentioned. It may be on 13th of May. 13th of May.
Final exam is 13th of May.
13th
As far
of
as
May. Yeah.
you told us.
At this time. But room is not this one. Room is Royal Hall 312. Royal Hall 312. I will give that notice, don't worry. Not at this room.
The small one?
That is small one. Because that was our original room. Then I changed talking with the staff here. But the register building knows that still that is the room. So they give it that room. 312. So don't worry, I will, yeah.
Is there like how many exams can you take in 24 hours for finals? Do they have like a rule for that?
Sorry?
Do you know if they have a rule for how many finals you can take in 24 hours?
Really? I don't.
I just have 3 in 24 hours, so I didn't know. If
You have 3?
Yeah. I don't know if I could take it
What?
early too, maybe.
3 in one day?
Well, the night of and then the next day.
Same to me. I have 3 exams.
You're
Oh.
teaching them all.
Same to me. I will start taking the exam at 4 p.m. I will finish at 8 p.m. Then next morning 8 a.m. I have another test.
Yeah.
Same, I think you have the same
Yeah, that you
courses.
teach them all.
Electronic circuits, digital electronics, and analog.
Yeah.
Oh, you have the 3 courses.
Yeah.
I don't know, I also asked him why this is something like that. So 4 hours in a row, then next morning, 8 a.m.
Oh no.
But here the problem is I cannot change this exam date. I tried. For example, the exam 1, exam 2 is in our control. We can take according to our, but the final exam, they decided they give the date, they give the time, you have to maintain it. Because same time have same, maybe if I want to take the exam earlier, I came here, but maybe another exam will going on here. That's why they just don't want to change. Okay.
But what about, why don't they allocate one day early for?
I don't know why they.
It's in the bachelor. We had this problem.
Even electronic circuit is actually at 11:30. Usually we take 11:30 on Tuesday. Usually they should give us the same time for the exam. Then we should have some gap. But it is now in a row. So I have an exam from 4 to 6, then again from 6:30 to 8:30, something like that.
You're taking 3 courses this time.
So, another was the flexible electronics. Okay.
Let me finish this
Yeah,
one.
sorry, yeah, we can continue. So, we are talking about now this programmable logic design. So as I mentioned, these programmable logic designs have different PAL, PLA. We'll talk about PAL in next class and PLA next class. Then we'll talk about a little bit about the FPG. That will be done. So today I'll just finish with this PLA. I have one more circuit. So you can try at first. Design a combinational circuit which will accept a 3-bit binary numbers. So it will accept 3-bit binary numbers as an input, and in a response, it will generate the square of the binary. Design a combinational circuit with the hero, which will receive at the input side 3-bit binary numbers, and in response, it will generate the square of these binary numbers. You don't worry, I will upload this just after the exam. Okay, let me draw the table first. At this, by this time, you can finish those things.
Food.
So this is the 3-bit binary inputs. You have to design this combinational circuit by using pure ROM, where we have 3 inputs and the output we have the square of these binary inputs. So if I get this output in decimal form, decimal equivalent, because it will be, it's supposed to be a square, right? So 0, 0, 0 means 0. So square will be 0. 0, 0, 1, 1, square will be 1. 0, 1, 0 is actually 2. Square will be 4. 0, 1, 1 is 3. Square actually 9. 1, 0, 0 is 4. Square is 16. 1, 0, 1 is 5. Square is 25. 1, 1, 0 means 6. Square is 36. 1, 1, 1 is 7. Square is 30. So this is the square of this binary. Now you have to find out the equivalent binary output. So to get this 49, how many bits we require? 6 bits we require. So we require 6 bits. 1, 2, 3, 4, 5, and 6. D5, D4, D3, D2, D1, D01, D3, 4, 5, 6. Right? So for 0, all will be 0, right? For 0, for 1, this one will be 1 only, right? This one will be 1. For 4, which one will be 1? This one, right? This is 0, this is 1, the binary bit, 4, no, sorry, 0, 1, 2, 8. Oh, did I make mistake? 0, 1, 2, 0, 1, 2,
0, then 2.
sorry.
0, 2, 4.
0, then 2, right?
Yeah,
4,
0.
8, 16, 32.
That 0 should be a 1.
1.
0 to 1.
Yeah, 2 to 0, 0. Yeah, thank you. So for 1 here, so for 4 is supposed to be here. For 9, 8 plus 1. For 16, it will be here. For 25, it will be 16 plus 8 plus 1. For 36, 32 plus 4. For 49, it will be 32,
16 and 1.
16 and 1. So this is the output. So you have to give connection accordingly, right? Okay. So interesting is here. Now, if you want to design this with a 8 times 4 ohms, p ohms, we should have only 4 outputs. But here we have 6 outputs. So we cannot make an 8 times 6, Usually the p ohms come with in terms of 4 bits. So 8 times 4 or 8 times 8 like this. So if you use the 8 times 8, then 2 will be unused. But here, we can use still this 8 times 4 p ohm. We can still implement this circuit by using this 8 times 4 p ohm. How? If you look at this circuit on the truth table, you can see here, this row is totally 0. That means this D2 connection, we can just connect it to the logic 0. And if you look at this connection, D0, it is 0, 1, 0, 1, 0, 1, 0, 1, finish here. So which is actually equivalent to the 0, 1, 0, 1, 0, 1, 0, 1, the LSB of our input. LSB of our input. So we still remain only D5, D4, D3, D2, 4. So we can think like that. So we have this address line. We can connect this D0 to here, something here, D0. we call it D0. D1 will be connected to logic 0. So D0, D1 gone. So D2, D3, D4,
D5.
Now you just need to follow this one. So D5 has the main terms for 6 and 7. 6 and 7, right? It's only 6 and 7. Mistake. For D4, we have 3 midterms. 4, 5, 7. 4, 5, and 7. For D3, we have 2 midterms. 3 and 5. 3 and 5. So 3 and 5. This one. And finally, for D2, we have 2 midterms, 2 and 6. 2 and 6. So, this is where we can implement actually any kind of program, any kind of Boolean functions by using this period. And this is how actually we design. Inside our IC, integrated circuit IC, so we already can imagine what is inside this. We have that MOSFET. And after that MOSFET, we have that fuse that is connected to each core. Yes. So as I mentioned, so we have 6 output side, but it is an 8 times 4 pylons. It has 4 outputs per gate. So how we can get the other 2? So what we have done, we see here this D1 is nothing but all zeros. So we can think that D1 connection is connected to logic 0 separately. And here this D0 is nothing but the replica of our input bits, the LSB 0, 1, 0, 1, 0, 1, 0, 1. So we just connect this D1 to, sorry, D0 to address line here. So we need the rest from D5, D4, D3, D2. So this is D5, D4, D3, D2. Now you have to implement this D5 according to the tuple. The D5 is high for 2 midterms, 6 and 7. The D4 is high for 3 midterms, 4, 5, 7. D3 has high for 2 midterms, 3 and 5. And finally D2 has 2 midterms, which is 2 and 6. So this interconnection means we are keeping intact the fuse, and others fuse will be burned. So we can program it according to our applications. Okay, so this is the design. I have all the circuit here. I will upload the hand notes. We can see here. So we'll finish here. So the last few lectures will be I'll finish early because we are almost finished. So we don't want to finish that we are just finished by this week or by Monday, and then because we cannot do that. So we will keep continuing like this. But I will try to think about your cases. So if we can finish by next week, then the final week we can just review. We can talk with us if you have any questions, if you have any things. And please go to your advisor, what they said. He or she told, please let me know, and I will also talk to them again. Yes, sir.
Can you repeat the last thing that you said?
The last thing is, are you talking about this?
No. I understood this part. After that, you said something.
So we can implement any logical function by using P1 or the programmable logic device. So there are 2 more different kinds of things. So some of you maybe didn't connect your axioms. I think you can, right? Again. Sorry.
Because I went to UMKC, I went to look at Portal, and
Yeah.
she might be wrong, she might have
Maybe, but on like the UMKC portal for your like your student, and it tells you like
2-year advisories and all that, it says it's hurt.
Did you get your exam today?
We have not,
You
no.
have
Yeah, but I got that, so the grade I got.
Thank you.
You wanna see what I got? Right, wrong.
Was it good?
You have your own or?
No.
Good. Round, where is round? Yours here. Okay.
Did I already talk to you about ethics? That ethics, he told me Monday that he's been,
Yeah.
ethics is good to take that test.
You have to choose the.
We're gonna ask him Friday when.
Collector, then maybe if it is not enough, maybe you can just write that this is
Thank
not
you.
one and it's not 15.
Oh,
That's
so,
okay.